All right, good morning. Welcome. Java 9 is primarily going to be about modules. This is probably not news to most of you here in the room. But as part of the bigger picture, well, how does this fit in? Because after all, Java is, oh my goodness, is 20 years old this year. I've been working on it for most of those years, which is, I don't know, maybe a mistake, I'm not sure. How is it that Java has lasted this long? Why is it still, so popular? Well, we've had a fairly basic method for evolving it. We identify a pain point in the platform, something that's affecting everybody who uses it, whether they're developers, deployers, or users. We figure out what the missing abstraction is, and then we add it to the platform. If we do this right, then it will look like something that has been there all along. Now, we can't always do that. Sometimes Java has been criticized for being a platform that wears its history on its sleeve, and that's largely because of the strong commitment we've always had to compatibility. But we've been reasonably successful here and there. Now, these abstractions might be big, like generics or lambdas, or they might be small, like a missing method or a class or a package. The point is to have a coherent evolutionary path where you figure out a motivation for something. We don't just do a feature because it's cool. We don't just add a language feature because, C# has it. We do it because it makes sense for the platform that we have and the platform as we see it going forward. We're always trying to preserve Java's key values of readability, simplicity, universality, and compatibility. So some examples of some of these big changes. I already mentioned generics. This was a big change in Java 5. The main pain point we were addressing there was the fact that until Java 5, most collections, you write code that manipulates collections, it was essentially dynamically typed. It was still strongly typed, but it was dynamically typed. You make a list of strings and you pull something out of it, well, all the compiler knows is it's an object and you have to go cast it to a string, which is tedious, and then you might make a mistake somewhere, and it's just, just very painful. Collections classes in particular became much easier to use once we had generic types. A second big change, a big change to the platform was the introduction of lambdas in Java 8. The pain point there was it was just enormously hard to express code as data, to move code around, to be able to abstract over behavior so that we could write frameworks that would make it easy to exploit large multi-core processors. So lambdas were the answer there. In Java 9, we're looking to address two pain points, and it turns out they have, we think, a common solution. One pain point is the class path, the brittle and error-prone class path. The other is the massive monolithic JDK. The missing abstraction and the common solution here is the introduction of modules to the platform. This is what we've been working on in Project Jigsaw and OpenJDK for a while now, and it's another example of a long-term investment in the platform. Most people know why the class path is bad by now. This problem is so infamous that it even has its own Wikipedia entry. You can look it up, jar hell. Jar hell is a term similar to DLL hell, used to describe all the various ways in which the class loading process can end up not working. Yep. Here's a class path. This is from Hadoop, which is actually a very well-engineered system. We've spent some time using it as a case study for modularization. There are 110 jar files on this class path. How do you tell if something's missing? Well, that's hard. How do you tell if there are any conflicts? Build tools like Maven can do a pretty good job based on artifact name, but if the artifacts themselves have different name but the same contents, there could be a conflict, and you won't find out until you have a nasty bug after your system has been up and running for 2 days. Is it safe to change an internal API? What's an internal API? This is the class path, right? The class path is, jar files are not components. This is the fundamental problem. Jar files are just containers. They're file systems on sticks. And you stick them in a row and you search them linearly from front to back looking for a class. The class path is a way to look up classes regardless of what component they're in, what package they're in, or their intended use. If you think about it, it's sort of amazing that systems like this even work, but they do. So there's the class path, there's the monolithic JDK. The monolithic nature of the JDK from the very beginning, well, at the beginning it wasn't so bad because it was really small, remember? But it's grown, it's big, and this pain point has several aspects. One is that it doesn't fit onto small devices. Even though small IoT-type devices, they have processors capable of running an SE-class VM, but they don't necessarily have the memory to hold all of the JDK, especially when your application is only going to use a little part of it. That's just a waste. It's even a problem in the cloud. Sure, big machines have plenty of disk space and plenty of memory, but in the cloud, it's all about optimizing the use of hardware. And if you've got thousands of images and each is carrying a whole copy of the JDK for an application that's only using a little bit of it, well, that's wasteful too. The JDK it's this monolithic system. It's grown up from the beginning as one system. Over the years, we've done what we could with the facilities that have been in the language from the beginning to try to keep components reasonably separate from each other, but there are inevitably some surprising connections because anything can refer to anything else. Somebody working on Corba over here can decide, oh, there's a convenient API over there in AWT. Oh, let's use it, no problem. Well, that makes sense when you're monolithic, but not so much when you're not. So we need tools to define proper components for the platform so that you can choose just what you need. Is the class path the right tool for the job? Well, no. As I said, jar files aren't components, and those annoying questions about is anything missing, is anything conflicting, how do you ensure consistency, is it safe to change internals? These aren't questions we want to have to ask about the platform itself. Related problem is, well, because there's no such thing as an internal API, we have a bunch of internal classes that people have used over the years in various packages whose names start with sun or have the string internal in them, ComSun internal, other internal things. And despite us having warned against using these for many, many years, there's a web page I found in the Internet Archive from 1998 that documents this. People have used them anyway. Well, they're convenient, base64 encoder. Sure, why not? It's there, it works. Cases like that are just for convenience and out of, I think, developer laziness. Other cases like sun disk unsafe, well, okay, fair. That's the only way you can do stuff like that. But the problem with these internal APIs is they become a significant maintenance burden for those of us who work on the JDK itself. They make it difficult to evolve the platform. Perhaps more importantly, they make it difficult to secure the platform. The JDK has lots of packages. Many of them are public. They're part of the official SE standard API, or they're supported for use as JDK-specific APIs. But many of them are private, all these things that start with sun dot. Those were never intended for outside use. And some of them contain very powerful APIs that can do nasty things like sun disk unsafe or reflection. When you're running in a secure environment, how do we keep potentially adversarial code from using this? Well, we've got one method, Dropline Security Manager check package access. If you forget to invoke that method somewhere to restrict package access, guess what? You may be looking at a CVSS10. That's no fun. Performance, finally, is another issue. Now, peak performance of Java is pretty good these days, but startup performance continues to be a frustrating problem. So, monolithic JDK, class path, scalability, maintainability, security, performance, the problems of the class path. We think the missing abstraction here, the common solution and the right tool for this particular set of problems is modules. Now, as proposed, modules are not a layer built above the platform on top of it. They're built deeply into it. They're a fundamental new kind of program component implemented in both the language and the virtual machine. They go well beyond the class path to provide two key features. One is reliable configuration, the other is strong encapsulation. How do modules fit into the ontology that we already know? Well, a module is a kind of a component. What kind of components do we already have? We have classes and interfaces. Classes and interfaces get organized into packages, and packages now get organized into modules. So a module is a collection of packages, a container of packages. It names the modules upon which it depends, and it can export specific packages for use only by the modules that depend upon it. How do we define a module? Well, we write a little bit of code. Here's a module declaration, a very simple module declaration. It says this is a module whose name is com.foo.bar. It names the modules upon which it depends. In this case, it requires some library module, com.foo.baz. It exports two specific packages for use only by the modules that depend upon it. It exports a package called com.foo.bar.alpha and another called com.foo.bar.beta. Okay, so this is a construct in the Java programming language. Where do you put it? Well, by convention, these declarations go in a file called module-info.java. This is kind of like package-info.java. The dash is there intentionally because that makes it an invalid class name. What do you do with a .java file? Well, of course, you compile it. You run javac, and you get a little class file. It's a compiled form of the module declaration. We call that a module descriptor. It has a somewhat different name in that form because we intend over time to be able to add additional information to it. You often have information at build time that's handy to put into a module descriptor, but would be inappropriate to put in the declaration itself. How do you package up a module? Well, we could define some entirely new format, but that would make adoption a really tricky challenge. So instead, what we've done is define modular jar files. So a modular jar file is a jar file, looks like pretty much any other jar file, but it has a module-info.class file at the root. The beauty of modular jar files is if you build them properly, you can make it so that a modular jar file can work as a module on Java 9 and later, and it can work as a regular jar file on the class path on Java 8 and earlier, because in those early releases, they'll just ignore the module descriptor. So we have our module com.foo.bar. It requires com.foo.baz, which also has its module declaration. And say we've got another module, com.foo.app, which is our actual application, and it uses the com.foo.bar library, and maybe it does some SQL too. Now, what about the platform itself? Where's Java-lang object? Where's Java-lang string? Where's I/O? Well, we use the same kinds of declarations to define those. We started with this graph many years ago when we began this effort. As you can see, it's quite the bowl of spaghetti. The important thing here is the base module way up there, in red. The base module is the module that you always need. It has fundamental things in it like Java-lang object and Java-lang system and Java-lang string. Now you might ask the question, okay, suppose I just want to print hello world. How many of the modules in the system will I need? And the answer is kind of depressing. Because, well, everything can refer to everything else. And so, my gosh, just to print hello world, I'll need a JAXP parser, I'll need Corba, I'll need some JDBC stuff. What's going on here? Well, what's going on here is a couple of decades worth of technical debt, which with over several years of painstaking work, we managed to clean up and eventually come up with something much simpler to understand. So this is the SE part of the module graph in the current Jigsaw prototype builds. As you can see, java.base, the base module, is at the bottom. Lots of things depend on it. If the base module doesn't depend on anything else, you want to print hello world, all you need is the base module. So this graph is defined by all of the dependence relationships amongst the SE modules. And as I said, these are defined in module declarations. Here's the declaration for the base module. It requires nothing. It exports a whole bunch of stuff. No surprises in this list. Every module implicitly requires java.base. You can write requires java.base if you want to, but if you don't, the compiler will insert it for you. Java.base is the only module that requires no others, and it's the only module that's known specifically to the language and the virtual machine. Now, how are platform modules packaged? Well, we could use modular jar files, at least for some of them, but many of the JDK modules have native code in them. They have configuration files and licenses and other stuff that you need to carry around. So we've devised a new format called JMod files. JMod files are sort of jar files on steroids. They handle native code and all of this other stuff. They're not intended really for execution. They're more of a transport format used to build the JDK and JDK-like images. All right, so we've got our three modules, an app module, a couple of library modules. We've got the platform modules, and we want to run our app. So all of these modules collectively, we'll refer to them as the observable modules. To make use of them at either compile time or runtime, and we try to treat both as uniformly as we can, we need to figure out how the modules relate to each other based just on what this app needs. So what do? Well, we interpret the module declarations by reading the module info.class files. We start with confu app. It requires confu bar, and it requires java.sql. Okay, so we're building a graph. And oh yes, it requires java.base, because every module requires java.base. We look at our next declaration. Confu bar, it requires confu baz. It exports some things, and it depends on java.base. Confu baz exports some stuff. It only depends upon java.base. Java SQL requires logging, everybody's favorite logging API, and Java XML and java.base. Logging only requires java.base. XML only requires java.base. And the base module itself requires nothing. We're done. Okay, so transitive closure. There you go. Very, very simple computation. So this graph expresses the notion of readable modules. So one module can read another if it's got an arrow to that module in this graph. Readable modules are the basis of reliable configuration. We can tell if something is missing. We can tell if something's duplicated. Let's look at the confu app module declaration again. Suppose we add requires confu whatever. Then we compile it, and we try to run this. Well, at compile time and runtime, there is no confu whatever module. Compile time, you'll get an error message, module not found. At runtime, you'll get an error message too. When you start the JRE, when you start the VM, module confu whatever not found, required by confu app. You don't get a class def not found error 10 minutes after your application started. You get this message right away. So that's reliable configuration. What about strong encapsulation? So strong encapsulation too is driven by the information in module declarations. Let's look at them again and annotate this module graph that we built. Confu app, it doesn't export anything. Confu bar, it exports confu bar alpha and confu bar beta. Confu baz exports this mumble package. SQL exports a couple of things. Logging exports logging. XML exports a whole bunch of stuff. And base exports even more stuff. So now we know not only how the modules relate to each other, but what each module exports to the modules that read it. This is how we get the notion of accessible types. Code in one module can only access a type in another module if that first module reads the second module and the second module exports the package containing that type. Accessible types are the basis of strong encapsulation. So here's an example. Suppose in the confu bar module, we have a confu bar beta internal package, only meant for internal use, and it's got some beta impl class that's used across the entire confu bar module, but is not meant for outside use. If confu app tries to import this and use it, what will happen? Well, at compile time, you'll get an error message. Beta impl is not accessible because package confu bar beta internal is not exported. If you manage to compile it by some subterfuge because your code is out of sync or whatever, and then you go to run it, you'll also get an error message, exception in thread main. I won't read the whole thing, but note that the error message tells you, we try to be very descriptive in these messages. They tell you what cannot be accessed, where it is, and why it cannot be accessed. So to recap, the essence of the module system: we have module declarations in module info.java files. We compile these into module descriptors, moduleinfo.class files. We package modules up either as modular JAR files, which are now proper software components rather than file systems on sticks, or JMod files for cases where we have native code. We have the notion of observable modules. We start with some set of modules that we wish to use some subset of. We run the transitive closure computation to resolve a module graph. That gives us the notion of readable modules. From readable modules, we get reliable configuration. And then finally, by interpreting exports, we have the notion of accessible types, which give us strong encapsulation. So these two properties, reliable configuration, strong encapsulation, are uniformly enforced at both compile time and runtime, so the configurations of large systems are essentially correct by construction. All right, going back to our pain points, let's see how modules help address them. Scalability, whether to small devices or large devices. As we've seen, modules let us use only what we need. How do we get rid of the stuff that we don't need? Well, to create custom runtime images that contain only what you need, we've developed a new tool, a tool that I remember asking James Gosling about 20 years ago. Why doesn't Java have a linker? Well, the answer was obvious at the time, right? It's mainly dynamic linking. Well, what we've done is we've introduced a linker, an optional linking step, with a tool called JLink. JLink takes in modular JAR files and or JMod files, runs the resolution algorithm, figures out the smallest set of modules that you need, and then creates a custom runtime image that only contains those modules. So if you have an application that only needs SQL, XML, base, and RMI, then you can build a minimal runtime that contains just those, plus your application, all in one nice tidy package ready to put in a Docker image or whatever you want. For performance, we've taken the opportunity to restructure the internals of the Java runtime to enable a bunch of interesting kinds of future work. So currently in Java 8, and this goes way back to 1.2, runtime is laid out this way. There's a bin directory, a lib directory, endorsed ext, rt.jar, and a bunch of other stuff. We've fairly completely redone this, so this is a change that is affecting tools and some applications into a cleaner form. We've separated out configuration files from the lib directory. They don't belong there. We put them in a place that makes it clear, okay, these are things that you can edit to configure your runtime environment. We've put things into the lib directory that are mainly intended, these are fundamental parts of the platform that you shouldn't mess with. If you do, then you're probably playing with fire. We've gotten rid of a number of things. The endorsed standards mechanism is gone, the extension mechanism is gone, rt.jar is gone. The platform's classes are no longer carried around in a jar file, which is pretty much the most inefficient format you could possibly choose to store classes in a runtime system. Instead, we've developed a new format, happens to be called JImage. It's very efficient, highly optimized, intentionally not documented because we want to retain the right to change it over time to make it better. So with this new format, this will enable all kinds of cool stuff. The JLink tool has plugins, for example, that make it possible to compress things in a custom way, to omit information that you don't need in your runtime. And we're also looking at how to integrate ahead-of-time compilation and ahead-of-time class data sharing, things like that, into this framework to improve startup time. Security and maintainability. So we are going to conceal most internal APIs of the JDK behind the strong encapsulation boundary defined by modules. This is going to break some existing libraries and applications. Now, we know that some of these internal APIs are very broadly used, and we know that lots of interesting products and libraries depend on them. So we're not going to take them all away right away. The ones that are very broadly used will remain available in JDK 9. We've been working for several years now on defining public supported replacements for those APIs. As these supported replacements become available, the old ones will fade away after allowing usually a full release cycle for people to adapt. Some of the more obscure internal APIs, which there's some evidence that some libraries or applications use, we're just going to hide. There is a way to get at them via a command line flag. To prepare for all of this, there's a tool called JDEPS. JDEPS is in JDK 8. There's an enhanced version of it in the JDK 9 early access builds. JDEPS is a sort of a Swiss Army knife of static analysis for jar files. You can run JDEPS on a jar file. You can ask it, analyze my use of JDK internals, and it will go through and tell you, at least from a static analysis point of view, what internal APIs are you using. It will even suggest what you should use instead. So if you want to start preparing for JDK 9 today, you run this tool on your jar files, figure out where you're using internal APIs, and work to remove those uses. Finally, the class path. Well, with modules and the module system, we're providing the tools so that you can bring the benefits of reliable configuration and strong encapsulation to your own code. But it's up to you to use them wisely. It's a long road ahead. We do not expect modules to be adopted as rapidly as some other features. We don't expect Java 9 to be adopted as rapidly as some other releases. And this is due to a few reasons. One is, well, 9 is going to be a fairly disruptive release. Concealing internal APIs, getting rid of some old crufty features. Yeah, some stuff is going to break, and that will slow adoption. Another reason is that, well, it's just the nature of the feature. Modules are not Lambda. Lambda was a jetpack, right? You could read about it, you could get going right away, you could write little examples, you didn't need to change a whole bunch of stuff in your system to leverage it. Modules are not a jetpack. Modules are more of a seatbelt. They make it safer so that you can build large systems more quickly, but it takes relatively more work to get going with them. So Jigsaw itself has been a fairly long road. We started working on this problem back in 2008. It has been a long road. There's a bit more left to go. It's an example of another long-term investment like generics or lambdas, where we see a pain point, we think we know what the missing abstraction is, but we take the time to get it right because we want modules to be a strong foundation for Java's next 20 years. So I have barely scratched the surface in the time I've had here. There's lots more to learn. My colleague Alan Bateman and I are giving multiple sessions this week to dig into Jigsaw in more details. Today we have Prepare for JDK 9, which is mainly about the incompatible changes in 9. Introduction to modular development is kind of the first baby steps into, okay, what is a module? How do they work? How do you use them in practice? Advanced modular development covers the problem of how to migrate an existing application, either from the top down or the bottom up, or some combination of the two. If you have additional questions that we don't answer in sessions, you can come to the Ask the JDK Architects session on Thursday. Alan and I will be there along with a couple of other folks from Oracle. You can ask us about Jigsaw or anything else if you like. And then finally, for the real rocket scientist level stuff, Project Jigsaw Under the Hood on Thursday covers the real science of modules in the module system, the semantics, how everything works in some detail. So this is a big change. It's still a proposal. We really value questions and feedback that we get here, so I encourage you to come to these sessions. For more information, all of our work is documented either in JDK enhancement proposals, which you can find on the OpenJDK website. There are 5 JEPs, 200, 201, 220, 260, and 261. And the module system itself is going to be a feature of the Java SE platform, so it has its own JSR, JSR 376. Thank you very much.